Hello, everyone. I'm Dorothy Reed, and really pleased to be here. I would like to thank the leadership team for the vision that they've just given us and the importance of networking. Okay. Anyway, so let's dive into the first of our 3 spotlight sessions. Each will bring you experts and emerging voices from across disciplines. Our first topic, the future of energy systems, and our first speaker today will be Dr. James Conca. He's a trustee of the Herbert M. Parker Foundation at Wazoo in the Tri-Cities. He has worked on nuclear and energy issues for 40 years at NASA, Washington State, New Mexico State, and Los Alamos National Laboratory. Conca has been an advisor to DOE, EPA, state and federal regulatory agencies, and to President Obama's Blue Ribbon Commission on America's Nuclear Future from 2010 to 2012. He obtained a PhD in geochemistry from Caltech in '85. We are.
Thank you so much, Dorothy, especially Maureen. A better title for this talk might be, "Don't forget about this stuff or you'll fail." Okay, so I mean, it's not the answer to everything, but if you do not understand this, you will fail. So anyway, I love these NASA nighttime shots because you can tell right away who has energy and who doesn't. It's what the fighting's all about, what's always been about, and what it always will be about. Right now, our species generates about 29 trillion kilowatt hours per year, but it's going to have to get a lot higher, and we'll talk about why. I'll use mainly the unit kilowatt hours because that's what comes at the end of the month in your bill. So Washington State happens to be the cheapest in the world for our level of lifestyle. It's going up a little bit, but everything else is going up a lot more. Now, the distribution of energy by type around the world, this is global, is about 2/3 fossil fuel, 1/3 split almost equally between nuclear and hydro. It's been that way for 40 years. It will continue to be that way for another 40 unless we make some serious changes. It depends on where you live, of course. The United States is 2/3 fossil fuel, 1/3 everything else, a little bit more nuclear, a little bit less hydro. This is weird because we have switched so many coal plants to natural gas that the relative number of gas to coal has flipped completely, which is good and bad. Washington State, again, is the least emissive of all the states because we have so much hydro and we have this wonderful nuclear plant that I live next to. West Virginia is the most coal, and Illinois is the most nuclear. Obama liked nuclear, he just wasn't allowed to talk about it. European Union, a little bit more nuclear because of France, a little bit less hydro. Korea is about almost 30% nuclear. Their plan, along with Japan's before Fukushima, but they're getting back to it, is to be 60% nuclear by 2050. And you might say, well, why? Well, Korea and Japan have no natural resources to speak of. They have no fossil fuel. They have their wind resource map is terrible. Their solar resource map is terrible. Their biofuels possibility is terrible. They don't make enough food to feed themselves. So unless you want to be completely dependent on China, Russia, or the United States for your energy, you need to go nuclear. China's interesting here. Doesn't look like much, but they are building a new nuclear power plant every month. They're breaking ground every month. Their last 5-year plan, which they tend to actually stick to, is to have 180 big nukes by 2035. And they are on track for that. So, this is the world power consumption growth curve. It's actually quite steep. Has nothing to do with us. We were last century. So again, right now we're about 2/3 fossil fuel. And the big question is, if you're going to address any of the environmental issues we seem to care about, then you're going to have to come up with an awful lot of non-fossil fuel, even just to stay where we are with fossil fuel, not to roll it back or anything, but just to stay where we are now. We're going to have to come up with more non-fossil fuel energy sources than we use fossil fuel now. So again, the numbers are big. You need to remember them, actually. They're huge. Now, the reason that curve is so steep is because of these people, still, almost 1 billion people have no access to electricity whatsoever. Close to 2 billion people still burn wood and manure as their main source of energy, and 3 billion more people are coming on board by 2050. And you might say, well, who cares about them? We have our energy, we care about the environment. Well, it turns out it's actually quite nasty to not give people energy. It takes about 3,000 kilowatt hours per person per year to lift someone up out of poverty. It was that way 300 years ago. It's that way now. It doesn't matter. You need about 3,000 kilowatt hours per person per year to have what we consider a good life, to be in the middle class. Now, I encourage you to visit the Human Development Index, UN, United Nations Human Development Index. It pretty much shows that access to energy is the first term in the equation of happiness. Not kidding. It's the first term in the equation of happiness. The second term is form of government. So if we look at this curve, it's actually kind of tight. And when we talk about people in the upper part, okay, we talk about energy strategy. We talk about reducing use, high-tech stuff, replace, bulbs with LEDs, electric vehicles, blah, blah, blah. It's to move them down, right? Now, the UK is probably the best per capita use. Of course, it's an island, but it's about 6,000 kilowatt hours per person per year. Notice I put California as its own country. Japan was about 16,000 in 1992, and mainly because of technology and cultural changes, they have come screaming down. So, it can be done. Now, Canada's big and cold. It won't matter what you do, okay? But that's okay. There's not that many people there. China's kind of funny because there's two parts to China. There is the 600 million still in poverty and the 800 million that are in the middle class. Since you're middle class, not the percentage-wise, but the absolute number of people in your middle class determines your economic and military power, who's going to dominate the second half of this century? You can shout it. I'll throw out some questions. You can shout it out. The answer is usually $1 trillion or China. So China, of course. Now, there actually is a sweet spot. If you can get everyone in the industrialized world down to about 6,000, get everyone else up to about 4,000. That is the minimum amount of energy to eradicate global poverty and its evil stepchildren, war and terrorism. Simple, but not easy. So here's, something like this has to happen. So you have the industrialized world, we cut them down, kicking, screaming to 6,000. No one likes to give up anything. But there's only about 1 billion people in that subgroup. There's a bunch of people at 3,000, keep them there. There's the developing world, you have to increase to 3,000, and the new people coming on board, you have to increase to 3,000. So at a minimum, you're going to need at least 34 trillion kilowatt hours, but since we don't equitably distribute things very well in this world, it's going to be well over 40. So what are the fastest growing energy sources in the world? Just shout it out again. Just shout it out. Loud. I was in one in the went to college in the 70s. Loud. I can't hear.
Nuclear.
I wish. No, I wish.
Yes.
Close. Close. This is kind of a trick question. I said energy, not electricity. Yeah, it's oil. Okay, so it's oil, coal, and gas. Okay, that's not in the right direction. These others, I know they're screaming up, no question about it, but they will not overtake the top three unless some radical changes. Now, this only goes to 2020, but in 2023, if you look at the United States, we increased gas capacity by 115 terawatt hours. Solar went up a little bit, and wind actually went down. So again, we are not going in the right direction here. We are not decarbonizing at all. So what do we mean by green? Is it carbon emissions? Is it the least environmental destruction, the least toxic chemicals produced, the least volume of hazardous waste, the least people killed or harmed? Is it reliability? If it's not reliable, it's not going to happen. Is it affordable? If it's not affordable, it's not going to happen. So again, there's more than one question, one answer to what's green, even though everyone thinks about carbon emissions as the major issue. So to answer this question kind of overall, the United Nations European Commission, Economic Commission for Europe, came out with a very nice comparison of life cycle issues concerning all the major energy sources. It was quite telling, actually. So first of all, in terms of carbon emissions, yeah, bad, good, bad, good. Okay, there's no question about this. I mean, fossil fuels are all about the fuel. It's all about the carbon. All the others have some carbon, but it's mainly in construction, very little in operation. Now, it turns out when you're looking at, this is for life cycle impacts on ecosystems, again, on the right, there's a bunch of perspectives, terrestrial ecotoxicity, natural land transformation, marine ecotoxicity, all the way down to terrestrial acidification. And it turns out, again, bad, good, bad, good. What's interesting is that hydro is split into two parts. Small hydro, less than 300 megawatts, and large hydro, which we have along the Columbia River, basically. And it turns out that large hydro is worse for the environment insofar as the backwater is so large that it generates a fair amount of methane and CO2, mainly in humid environments. So in eastern Washington, it does not generate a lot of that. But it has to do with the size of the backwater. Still better than coal. For all the others, they're all quite low. Nuclear happens to be the best, but they're all quite low. Same thing with life cycle impacts on human health. Bad, good, bad, good. If you're talking about photochemical oxidant formation, particulate matter formation, all the way down to ionizing radiation, and even for climate change, again, fossil fuels, all about the fuel. That's all about the emissions. All the others are about construction and other things like that. But again, nuclear's the best. Just happens to be the best. But they're all good on this side. Now, if you want to look at mortality, the death print, deaths per trillion kilowatt hours produced, you have to normalize to production, not to installed capacity. That means nothing. You need to actually look at what it's producing. So coal, again, if you need an evil, coal's evil if you need it. Yeah, so China's actually getting better. That number was about 250,000 a few years ago. They're getting better. The United States is much, oops, I'm sorry, the computer's jumbled a little bit of the column. We only kill 10,000 people per trillion kilowatt hours produced, only 10,000. It's supposed to get either a guffaw or something. Oil, natural gas, biomass. Biomass is kind of funny because the World Health Organization just recently categorized it as a developing world epidemic because of poor ventilation. If you're going to burn stuff inside your home, your hut, whatever, you have to have good ventilation, or you have a lot of upper respiratory effects, just like that's what coal is, essentially upper respiratory effects. Now, solar on down, those deaths are all accidents. They're all accidents. So I'm so sorry about the lower number there. So hydro, now this is global, so 1,400, sorry. Hydro in the United States, 0.1. Nuclear global, and I included a ridiculous number for Chernobyl, but that's okay. Nuclear US, 0.1. How come, for the three we have, coal, hydro, and nuclear, why do we kill fewer people? Shout it out.
Concrete.
We have good concrete, yes, very good. Not as good as we had in 1950, but really good. Anyone else? Regulation. Regulation. So, I mean, I'm a regulatory hound. I love regulations. If you look at hydro, well, I'm sorry, let me back up to coal. Why is coal so much better? What regulation is that?
Scrubbers.
The law, going back. In history, the single law that has saved most lives is the Clean Air Act. And that's why that's so much lower. So when anyone starts talking about changing the Clean Air Act, I want to strangle them. Oops, sorry. Next, hydro. What about hydro? FERC. Oh, right. No one ever gets that. This is a good crowd. Of course, Maureen said it would be. So the Federal Energy Regulatory Commission, they actually check dams. In fact, one out near me, Priest Rapids, a few years ago, they had to shut down because there was a couple of cracks in the concrete. Now, in most other countries, it just fails. That's the first indication that there's a problem. And it'll basically take out villages and stuff like that. So if anyone remembers the 1976 Bankyo dam failure in China, killed 171,000 people. That's serious. In the United States, that 0.1, that's one person fell off a dam, fell off scaffolding and broke his neck. Nothing to do with hydro. Nuclear, the same thing. NRC, the Nuclear Regulatory Commission, it is the most strict regulatory agency for anything in the world. I love it because a lot of people say, oh, it's in the pocket of the industry, and the industry wishes it was in its pocket because they'll shut you down for nothing. And so, again, that 0.1 was someone at Browns Ferry, fell off some scaffolding, broke his neck a few years ago. So again, if you care about human life, sometimes lately I'm not, but if you care about human life, there's no question renewables are best and nuclear is the better one. Let's see, what do I got? How much time do I have? Oh, good. Capacity factor. Now, this is something that most people don't know about. You might probably have a good idea about it. But this is the annual average percentage of the maximum output possible. Okay, so if you have a 1 megawatt wind turbine, and throughout the year, the average is going to be 0.35 megawatts, not 1. It will never produce 1 megawatt all year long, right? Because the wind doesn't blow and sometimes and all that kind of thing. Same thing with solar, same thing. Hydropower is kind of funny. It shouldn't be this low, but water is used for so many things like transportation, like irrigation, flood control, things like that, that you can't use it to produce energy all the time. Okay, so it only is about 40% on average, of course, in the United States, and even our huge ones here. Coal, you just have to fuel a coal plant continuously. 1,000 megawatt coal, well, the one at Centralia that we just closed, half of it, and then the other half is closing soon, if it's not already closed. Every day, 100-ton coal cars rolled into that plant every day. 10,000 tons of coal every day. Now, that's weird, but it also takes time to change that out and to refill, so that's why it's about 50%. Natural gas is about 60%, except could be higher, except that it turns out there are parts of the day when natural gas is very expensive to produce electricity. So they don't want to produce electricity then, and that's an issue with the grid in general. And then nuclear, it's over 90%. It just runs all the time, except every other year you shut down for a month to refuel. Now, if you want to compare this, and it depends even then where you are in terms of wind and solar. The average wind capacity in the United States, in the United States is 34%, but in Washington State it's only 27%. So you really shouldn't be building wind turbines in Washington State very much. But Tornado Alley, up the center of the country, gets much more energy per megawatt of wind turbine than anywhere else. So you should be building that there and then using high voltage transmission lines to get it out to where it needs to be. You shouldn't be building wind in Georgia. It's a technical term for that. It's called dumb. But that's okay. Now, whoops. Let me back up a little bit. So if you want to compare systems, especially for cost, people, they always say what's expensive, what's not expensive, but they never compare the right thing. So if you have to, again, normalize to the output. So 1,000 megawatt nuclear power plant with this average capacity factor times 8,766 hours in a year produces about 8 million megawatt hours per year. That's it. No more. It may be a little bit less if there's mechanical issues, but no more. Wind, the same thing. Same size, emplaced farm produces only about 2 million. So if you're going to, unless you're in Tornado Alley, then it's like 4 million. But if you're going to compare nuclear with wind, you have to do this. So if you're going to compare cost, you need to compare 4,000 megawatts of wind with 1,000 megawatts of nuclear. But it gets a little worse because the lifespans are quite different. The design life of a large nuclear power plant is 80 years, not 40. 40 was just a number picked out of the air by the Atomic Energy Commission in 1957. We should relook at the license. That's all. It has nothing to do with the design life. In fact, most of ours are now licensed for 60 years, and now we're starting to get applications for 80 years, which is fine. Wind is about 25 years. I've yet to see one actually go 25 years, but that's the design life. And it only produces about 60 million megawatts over its life, megawatt hours. So again, if you're going to compare these cost-wise, you need to compare 10,000 megawatts of wind with 1,000 megawatts of nuclear. Okay, so last thing, how do we achieve a low-carbon future in Washington State? We kind of already have it, but something like this. You need to get rid of coal and gas. I mean, if you're going to decarbonize, you got to get rid of coal and gas. The problem is we're building gas plants like crazy, and no one is going to shut down a perfectly new gas plant, all right? So every gas plant we build now, we're in it for 40 years, at least. That's one of the issues. So all we need are 3 small modular reactors to double nuclear in this state. And we have a lot of small nuclear reactor companies in the Pacific Northwest. Hydro go down a little bit, and we can triple renewables, and that's a reasonable mix, especially since our generation is going to grow. Now, I'm not including data centers and AI in this, so that 115 terawatt hours is going to get much bigger. And right now, we have a minuscule grid-scale storage, so it's, you need grid-scale storage, and we only have about 170,000 EVs. If you're going to tackle petroleum, it's going to be EVs. And I mean, yeah, hydrogen is coming, ammonia coming. They're not there. The infrastructure is not there. But we know how to make electricity. So with 15 grid-scale storage units of about that size and over 2.5 million EVs, which themselves will take 7 terawatt hours a year to charge, we can decarbonize. Now, it's going to cost the state about $200 billion by 2035. Sounds like a lot. It's not. It's the same amount we'll do anyway if we do not make any changes. That's the business as usual. It's just the same price. The problem is when you decarbonize, your capital investment goes up because instead of buying fuel, you're buying things. You're making concrete. You're making towers. You're making stuff. And that takes upfront capital investment, and no one likes to do that. And just saying, hey, do it now, you'll benefit later. No one believes that. Unfortunately, that's the way with renewables and alternative fuels. It just takes a lot to build. Then it is cheap. Thank you.